Hello, today we are going to study logistic regression-based classification. In logistic regression-based classification, a logistic model is developed from training data to aid the classification task. I will explain it all here in this video. To understand logistic regression-based classification, we need to make sure that we understand linear regression well. We'll first study linear regression and then we'll move to logistic regression-based classification. Let's discuss what a linear regression model is. Let us say that we have a data set, and in this data set there are two columns. In the first column we have the amount of crops harvested, and in the second column we have amount of water. There are some associated units, maybe 1,000 gallon per day or something like this. And crop harvested would be in a certain area, how much crops are harvested in a particular season. So let's say that when we have 5 amount of water, in that case the amount of harvest is 10. When we have, let's say, 6 amount of water or 6 units of water, we have a harvest amount of 12. When we have, let's say, 8 units of water, in that case we have a harvest of 16. Now can you answer this? What happens if we have 9 amount of water or 9 units of water? What should be the yield here? What should be the amount of crops harvested in a particular season? If you answered 18, you are correct. In your mind, you actually built a model that the crops harvested, if it is Y, and if the amount of water is X, you know that Y is equal to 2 times X. So in your mind you created a model. In this model, the only item that you need is 2. This is a model parameter. The purpose of any type of regression, such as linear regression, is to come up with such model parameters. Let's make it a little bit more complex. Let's change this dataset entirely. Let's say that for 5 units of water, the harvest amount is 11. For 6 units of water, the harvest amount is 13. For 7 units of water, the harvest amount is 15. For 10 units of water, the harvest amount is 21. Can you tell me what would be the harvest amount if the unit of water is 9? If you answered 19, then you are correct. In your mind, you have built up a model. The model says that if this column or this variable is X, and if this column or this variable is Y, then the model is Y equals 2X plus 1. Notice that when you have this 5, basically 11 is equal to 2 times 5 plus 1. For this 6, 2 times 6 plus 1 is 13, so Y here is 13. For 7, you have 2 times 7 plus 1, which is 15, so you have 15 here. Then for 10, you have 2 times 10 plus 1, which is 21. Then for 9, you have 2 times 9 plus 1, which is 19, and 19 is here. If you were able to answer the questions associated with these two rows, like when the amount of water is 10, what would be the amount of crops harvested, and if the amount of water is 9 units, then what would be the amount of crops harvested? If you were able to answer these questions correctly, that means that you are already familiar with linear regression. When you are looking at this data, you are building a model in your mind, and this model is y equals mx plus c. And this particular model, y equals mx plus c, is directly associated with all these equations you have here. So that means for this particular data set in your mind, you have selected 2 for m and you have selected 1 for the c. And if you remember from geometry or linear algebra, this particular equation is a linear equation, because if you plot all your data, then you will obtain a line like this one, where actually the horizontal axis is x and the vertical axis is y. Basically, the part m indicates the slope of this particular line. C is the vertical intercept. So this c is a constant, and of course this m is the slope, which is also a constant for your linear regression model. Given this particular data set, the target is to come up with m and c, and that is what your model is. When you come up with m and c, basically you can answer what would be the amount of crops harvested given the amount of water. Here in this example, this particular column is called an independent variable, and this particular column, that is y, is called a dependent variable. The dependent variable here is dependent on x. This is why it is called dependent, and the independent variable does not depend on anything. Well, the independent variable depends on the money the farmer can spend, but basically that amount of money is not present in this particular table. As a result, we have to consider that based on this particular table, this second column is the independent variable and this first column is the dependent variable. Let us discuss this further. Let's say that we have this particular data set with 5 rows and 2 columns. Again, this second column is our independent variable, and the first column is our dependent variable. The second column, the independent variable, is water amount provided in the crop fields, and the amount harvested is the dependent variable y. If we plot this, we obtain this graph. In the horizontal axis, we have x, and in the vertical axis, we have y. If we take a closer look, we'll see that this particular table has the form y equals mx plus c equals 2 of x plus 1. That means that m is equal to 2 and c is equal to 1. So this is the model. Each of these points in the graph associates with one of the rows here in the data. The line is actually a very straight line which will go through every point in the data we have. In real data, data points really do not fall on top of one single particular line. Let's take a look at an example. Let's say that our y, or the dependent variable, has slightly different values. Let's say that for a water amount of 5, the harvest amount is 10. For water amount of 6, the harvest amount is 15. For water amount of 3, the harvest amount is 8. For water amount of 8, the harvest amount is 20. For water amount of 10, the harvest amount is 22. After plotting this on a two-dimensional graph, we obtain this. And notice that these points really do not fall on top of one single line. And this is the nature of real data. Real data really does not follow a particular single line. The best we can do is we can try to draw a line which would be very close to all of these points. If we draw this line, is it a good line to represent all these points? If your answer is no, you are correct. If we, instead of this line, if we draw this line, will it be a good line to represent all these points? If you answered no, then your answer is correct. Now, if we draw this line, is this a better line than the two lines we drew before? If your answer is yes, then your answer is correct. Now, why is this line a better line than the two lines we drew before? This line is a better line because all the points are very close to this particular line. And these amounts that are drifted from the line, this amount is called an error. Basically, the purpose of drawing such a straight line is to reduce these errors. These errors are computed based on from the point you draw a perpendicular line on the linear model. This is the linear model line. For all the points, you sum up those errors, and your target is to minimize that summation of errors. This is the task of linear regression. You try to come up with the best y equals mx plus c. You will try to come up with the best m and c in such a way that all these errors are minimized. Let's take it to the next level. The general idea is we write y equals beta naught plus beta 1 x1 when you have one independent variable and one dependent variable, something like this data. Here, this beta naught is actually this intercept c, and beta 1 is this slope m. This is only when you have one independent variable, this one. But what if you have multiple independent variables? For example, we could have another column here which states amount of sunlight. I don't know the unit of sunlight, but let's say that we have some sort of unit there, and we have more information like 3 here, 2 here, 9 here, 7 here, and 4 here. For this particular specific 3 units of sunlight, 5 units of water, the harvest is 11. For 2 units of sunlight per day, for 6 units of water per day, the harvest amount is 13, so and so forth. In that case, we extend our equation for our dependent variable in such a way that we include even the second variable. So let's call the water amount to be x1 and sunlight to be x2. In that case, y is equal to beta naught plus beta 1 x1 plus beta 2 x2. So this is still a linear equation. We have two independent variables right now, and we have one dependent variable. For three independent variables, our equation would look like y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Notice here that with this equation, our dataset would be four-dimensional data, where we have 1, 2, 3 independent variables, or 3 columns that represent the independent variables, and 1 column for our dependent variable. This particular dataset, this one is actually represented by this equation, this particular equation, because here we have 1, 2, 3 columns, and here we have 3 variables. One is the dependent variable, and the other one is one independent variable, which is the water amount, and the other one is the sunlight amount, which is the second independent variable. For a 5-dimensional dataset where there is one dependent variable and 4 independent variables, the equation will look like y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. The general equation would be y equals beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta n xn. For this equation, number of columns you have in the data is equal to n plus 1. Among those n plus 1 columns, n columns represent the independent variables and 1 column represents the dependent variable. Notice that with a dataset of n plus 1 columns, you will have n plus 1 coefficients, starting from beta naught and ending at beta n. Now, this particular general equation is a linear equation. That means this equation has a maximum degree of 1. That means all these independent variables, this has a power of 1. So x1 has a power of 1, x2 has a power of 1, x3 has a power of 1, xn has a power of 1. If we had in any of these independent variables a maximum power of 2, then we would have called this equation a quadratic equation. If we had in any of these independent variables a power of 3, we would have called it a cubic equation, so and so forth. This is a polynomial equation regardless of the degree, but here the maximum degree in the variables is 1. As a result, this is a linear equation. In a linear equation, the maximum power of the independent variables can be 1. Now let's say that we have a data set where we have the dependent variable y and we have one independent variable named x, or in a sense we can call it x1 if we want to make sure that it matches with the general formula, because in the general formula the first independent variable we have is x1. Now let's actually write down the elements of the data. For 1 we have 6, for 2 we have 5, for 3 we have 7, and for 4 we have 10. So this is the data. Now for this data, obviously the equation would look something like this: y equals beta naught plus beta 1 x1, and our objective here is to find out these two variables from all these 4 items. Now, if we believe in this equation, that means if we are going to build this linear model, then we have to come up with equations for each of these lines. And this is y, so we can write 6 because y is 6 based on this particular line. 6 equals beta naught, which we still don't know, plus beta 1, which we still don't know, then times x1, and x1 for this particular row is 1, so we make it times 1. So this particular equation is coming from row 1 of the data. Similar to this, from row 2 we come up with y, which is 5, equals beta naught, which is something that we still don't know, beta 1, which is still we don't know, then x1 is 2 in row 2. Then for this particular row, the third row, we have 7 equals beta naught plus beta 1 times 3. For this particular row, we have 10 equals beta naught plus beta 1 times 4. So in these 4 equations, we have 2 unknowns. The 2 unknowns are beta naught and beta 1. The purpose is to find out 2 unknowns from these 4 equations. Notice that we could have millions of entries here in this dataset. For 1 million rows in the dataset, we will have 1 million such equations. We cannot use just 1 or 2 equations. We have to use all 1 million equations to come up with our best beta naught and beta 1. In a perfect world, the left side of every equation would be the same as the right side. As a result, the equation can be rewritten as 6 minus beta naught plus beta 1 equals 0. Similar to this, the second equation can be rewritten as 5 minus beta naught plus 2 beta 1 equals 0. The third equation can be rewritten as 7 minus beta naught plus 3 beta 1 equals 0. The fourth equation, which stands for the fourth row of the data, can be rewritten as 10 minus beta naught plus 4 beta 1 equals 0. Using these 4 equations, we have to come up with the best values for 2 coefficients beta naught and beta 1. So in this case, our unknowns are beta naught and beta 1. Again, if our dataset had 1 million rows, from those 1 million equations, we had to come up with 2 unknowns, beta naught and beta 1. For these 4 equations, we can easily take the square in the left side and square in the right side. So we are taking squares in the left side and squares in the right side. Then we will sum up all the squares of the left sides and all the squares of the right sides. As a result, we will have 6 minus beta naught plus beta 1, then square, plus 5 minus beta naught plus 2 beta 1, then we have a square, then the third equation would be 7 minus beta naught plus 3 beta 1, then a square, then we will have plus 10 minus beta naught plus 4 beta 1, then we have a square, and the entire summation would be equal to 0, because in the right side you will have 0 square plus 0 square plus 0 square plus 0 square. This is one single equation that consolidates all those four equations. That means this one single equation consolidates the entire data. So if we had 1 million rows in this data set, then we would have 1 million equations. But after we do square the left side of each of these equations and sum them up, we would always have one particular equation. And that one particular equation will consolidate all the information provided in the dataset, or in another sense, that will add all the errors we have associated with each of the equations. That means with each of the rows. We already talked about the errors in this video. Now if you do a summation, if you expand this one, you will get 4 beta naught square plus 20 beta naught beta 1 minus 56 beta naught plus 30 beta 1 square minus 154 beta 1 plus 210 equals 0. This is the equation that consolidates all the equations generated from each row of the dataset. Notice that this equation has only two unknowns, beta naught and beta 1. This equation is a quadratic equation because we have a highest degree of 2. And from a quadratic equation that contains two unknowns, such as this one, it contains two unknowns, beta naught and beta 1, we will be able to figure out what the values are. One easy way is to take partial derivative with respect to one unknown and then also take partial derivative with respect to another unknown. Let's call the left side to be s. Let's take partial derivative with respect to beta naught first. So we will have 8 beta naught plus 20 beta 1 minus 56. And in the right side also, if you take partial derivative with respect to beta naught, you will receive 0. Now let me explain this one. If you take partial derivative of this particular term, it will be 8 beta naught. If you take the partial derivative of this term, it will be 20 beta 1. If you take a partial derivative of negative 56 beta naught with respect to beta naught, it will be 56. If you take partial derivative of this term with respect to beta naught, basically with respect to beta naught, this particular term is a constant, so this will become 0. This part does not have any beta naught, so a derivative of this part with respect to beta naught will be 0. This is a constant. As a result, the partial derivative of this part will be 0. Similar to this, if we take partial derivative of s with respect to beta 1, we obtain the following: 20 beta naught plus 60 beta 1 minus 154. If we take the partial derivative of the right side, we will have 0. Now we have two equations, this equation and this equation, and notice that in these two equations we have two unknowns, beta naught and beta 1. If you solve these two equations for beta naught and beta 1, you will obtain beta naught equals 3.5 and beta 1 equals 1.4. In a linear regression model in which we have one independent variable and one dependent variable, the equation is y equals beta naught plus beta 1 x1, as we already know. In place of beta naught, we'll be putting 3.5, and in place of beta 1 we'll be putting 1.4. Then we will have the independent variable x1. As a result, our model equation is y equals 3.5 plus 1.4 x1. That means at any time point, if x1 is provided, then we will multiply that x1 by 1.4 and we will add 3.5. We will obtain y. Now notice that in this entire practice we just computed the value of beta naught and the value of beta 1. These are the two model parameters for linear regression with a two-dimensional dataset where we have one independent variable and one dependent variable. For more independent variables, we have a more general equation like this one. Given a high-dimensional dataset, you can use programming tools like MATLAB to compute the associated coefficients beta naught, beta 1 up to beta n, depending on how many dimensions you have. In summary of this linear regression practice, beta naught is equal to 3.5 and our beta 1 is equal to 1.4. As a result, our model equation is y equals 3.5 plus 1.4 x1. If x1 is the amount of water and y is harvest, now if someone asks us, okay, if I apply 6 units of water, then what will be the harvest amount? We'll say that, okay, we can answer your question. Y, which is the harvest amount, will be equal to 3.5 plus 1.4 times 6, which is provided by the user, is equal to 11.9. Therefore, we can answer the client or the person that, okay, with an amount of 6, your harvest will be 11.9 unit next season. This linear regression concept is widely used for prediction purpose. We could have many more columns. As long as we have computed all our beta values from historical data, we will be able to compute y based on whatever linear equation we have. We will plug in any new data that we haven't seen before and we will be able to predict what the y value would be. This entire practice actually explained how to reduce these amounts of error, how to find out the best possible line that fits the entire data. You might have heard the term model fitting or line fitting. Through this exercise, we found the best possible line which will minimize all these errors for a given particular dataset. Therefore, the concept of regression is to generalize the data to a particular model, in this case to a particular line. This is why it is called a linear regression model. So far, we discussed linear regression. Now, we will be discussing logistic regression. In parallel, we will be discussing logistic regression-based classification. One added piece of information is that logistic regression-based classification is suitable only for binary classification. That means in the data there can be only two class labels. Let's assume that we have this particular data set, where in the first column we have some level of blood factor, which are 10, 30, 45, 57, so and so forth. And for these blood factors, in the second column we have the labels, whether the person who has a 10 blood sample or 10 units of factor in the blood is a corona infected patient or not. And we have yes or no labels in this part. Therefore, this first column is actually x1 in our linear regression model, and the second column is y. In our linear regression model, we cannot directly use yes or no. we will be using a number to represent yes or no. In this case, yes would refer to 1 and 0 would refer to no. That means yes indicates coronavirus positive and 0 indicates coronavirus negative. Now both the columns have numerical values. Now if we plot this data, that means in the horizontal axis if we put x1 and in the vertical axis if we put y, we receive this particular plot. Notice that in the horizontal axis we have this particular blood factor, and in the vertical axis we have either infected or not infected, that particular information. 0 indicates not infected and 1 indicates infected. 10-0 is right here, 30-0 is right here, 99-1 is right here, similarly 87-1 is right here, so and so forth. So all these points are actually coming from this particular data set. Now consider that we want to build a linear regression model. That means we want to come up with a line that best fits the data. The line can be like this one, the line can be like this one, the line can be even like this one. Which line it should be, it depends on the analysis of those beta values. Obviously in this case, since we have two columns, we will need beta naught and we'll need beta 1. Let's say that this line fits the data very well. That means this line will contain minimum amount of error from each point toward the line. Now notice that with this line, if we go for prediction and if our data contains a blood sample value with a factor of 120, the corresponding score will be very up in this direction, because this line, if you extend this line upward somewhere, it will be meeting here. So the value will not be very close to 1, rather it will be very, very far away from 1 in the positive direction. Similarly, if in a sample we find that the amount of that particular factor in blood is 30, then basically 30 is somewhere here. Therefore, the infected or not infected column will crisscross here. As a result, the predicted value, that means the y, will be far negative. So in a sense, we can say that if this line gives us a negative value for y, then for sure the sample should be treated as not coronavirus infected. That means negative. If we find a very, very, very large value, way greater than 1, then basically we can say that it's a positive sample. That means the patient is infected with coronavirus. But notice that there is a confusion zone in this area. If we have a blood sample with, let's say, 62 factor in the blood, so 62 will be somewhere very close to here, 62 crisscrosses here. So what should we consider? Again, this is just a drawing. We still don't know what our particular beta naught and beta 1 values are, so we don't know whether this line is a perfect one or not. Therefore, it is really difficult from a line to understand whether the data is speaking for a particular sample as positive, or is it supporting the new sample as a negative one. It would be more logical to create a probabilistic model where we can say whatever new sample we get, what is the probability that this new sample is coronavirus positive. To accomplish that, if we can convert this linear line to some sort of probability which varies from 0 to 1, then we can say that we have converted this linear regression line or linear equation to something probabilistic. If a patient has 50 units of some blood factor, then basically from 50 we will draw a line and we'll see where it hits the probability line. The probability line is very close to 0.19. Now we can say that the probability that the patient who has a factor unit of 50 in the blood sample has a probability of 0.19 to be considered as coronavirus infected. That means the probability is too low, so the patient is probably not a coronavirus infected patient. Similarly, if we find that a sample contains a blood factor amount of 70, then with 70 we draw this line and we see that the patient has around 0.83 probability of being infected. That means the patient is highly probable to be coronavirus infected. In a sense, we are saying that if we find that the probability is greater than 0.5, then we will declare the patient as infected. If we find that the probability is less than or equal to 0.5, we declare the patient as not infected. Now, where is that threshold to declare a patient as infected or not infected should be decided by a health professional or based on some other research which will include health professionals. Here, without any particular information, we are assuming that 0.5 is the threshold, but in practice this threshold might be changed by a domain expert. Now the question is, how do we convert this linear function to this probabilistic nonlinear line? Luckily, we already have an existing function in math or in statistics which is called a logit function that represents the exact same idea. For numbers which are negative, the function gives values very close to 0, and for large numbers which are positive, the function eventually gives numbers close to 1, and at 0 the function gives 0.5. Therefore, this spectrum varies from 0 to 1. As a result, we will be able to utilize this logit function as our probabilistic function for the linear model. This logit function helps us convert the linear combination of the independent variables to a logistic function model. Let's say that there is a way to compute beta naught and beta 1. The model parameters for this line would be beta naught and beta 1. That means our equation is y equals beta naught plus beta 1 x1. Of course, this column is y and this column is x1. And here all no's would indicate zeros, ones would indicate yes. Based on the logistic regression function we have here, we can write the probability that the person is infected. That means the probability that the person has 1 is equal to 1 divided by 1 plus e to the power minus beta naught plus beta 1 x1. In general, the function is the probability that the sample is positive or the sample is 1 is equal to 1 over 1 plus e to the power minus whatever linear regression model you have. If the linear regression model has many beta values, you will be able to incorporate all of them right here. So the general equation would be beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta n xn. That means if your data has n plus 1 columns, then you will be using this particular equation. That means for this particular data set, this is our equation. If someone comes with a blood sample that has 45 units of factor, the probability that the person is infected is equal to 1 over 1 plus e to the power minus beta naught plus beta 1 times 45. If someone comes with a factor of 62, then the value would be 1 over 1 plus e to the power minus beta naught plus beta 1 times 62. So this value is actually the x1 value. If we already know beta naught and beta 1 for this particular line, then definitely we can come up with all these probabilities. For this particular line, I already pre-computed the beta naught and beta 1 values. Beta naught is equal to negative 7.9432 and beta 1 is equal to 0.1229. With this calculated beta naught and beta 1, we will be predicting whether a person is infected or not for any blood factor sample. For example, what is the probability that a person is infected given the sample has 45 factors? Basically, the equation would be 1 divided by 1 plus e to the power minus beta naught, which we already know, which is negative 7.9432 plus beta 1, which we already know, 0.1229 times x1. X1 here is 45. So we have 45 here. After pressing the buttons of a calculator, I find that the probability is 0.0822. That means if a person has a blood factor unit of 45, then the probability that the person is infected is this, which is pretty low and far below 0.5. As a result, the person is not considered as infected. Let's do a similar calculation with the value 62. The probability that the person is infected, if the person has an amount of 62 factor in the blood, is 1 divided by 1 plus e to the power negative 7.9432 plus 0.1229 times 62. After pressing the buttons of a calculator, we find that this is 0.4198. This indicates that if a person comes with a factor of 62 in the bloodstream, the probability that the person is infected is 0.4198. If our threshold is 0.5, this number 0.4198 is below the threshold. As a result, we declare that this person is not infected. I should mention that all the data sets I have used here in this video are fictitious data. They are not real data. Let's do these calculations for two more values. What is the probability that the person is infected with coronavirus if the blood factor contains 75.3 units? So let's plug in all the values we know. That means beta naught and beta 1 values and also the x1 value in this particular equation. Beta naught is negative 7.9432, beta 1 is 0.1229 and x1 is 75.3. The calculated value is 0.7877. Since this value is greater than 0.5, we consider this person as infected. For another value of 85.1, let's check if the person is infected. Obviously the person will be infected because 85.1 is greater than 75.3, and with 75.3 the patient was infected. Therefore with 85.1 the likelihood that the patient would be infected is high, because our logistic regression function monotonically increases with higher value of independent variables. But still, let's do the calculation. After we do the calculation, we would see that the probability is quite high, 0.9252. Therefore the person is infected with coronavirus. In MATLAB there is a function called glmfit, which would help you compute all the beta values from training data and training labels. In glmfit you will have to provide the training data, and also you will have to provide the training labels. You have to additionally provide some other parameters. Let me write down those parameters here. I'm not explaining all the parameters here. The crucial parameters you need in glmfit is training data and the labels. This is particularly a matrix. The matrix contains all the independent variables as a matrix, so the original data is here, and this labels, it's actually just one column. We will have either 1 or 0 against every row here in this particular column data. Of course, you will not write down these feature names in the data of training and labels. glmfit returns all the coefficients. That means all the beta values. So if you have 4 independent variables and 1 dependent variable, that means in the coefficients you will have 5 values varying from beta 0 to beta 4. Logistic regression based classification is very powerful. In real data sets it has high accuracy. It is a binary classification mechanism. This classification technique relies on linear combination of the independent variables. It uses a standard logit function to convert the linear combinations to probabilities. The example we discussed in this video for logistic regression is basically a two-dimensional data set. That's why you had beta 0 and beta 1 in the logistic regression function. If you have a three-dimensional dataset, then you will need beta 0, beta 1 and beta 2. With a four-dimensional dataset where you have 3 independent variables and 1 dependent variable, in that case you will need beta 0, beta 1, beta 2 and beta 3. I hope the concept of logistic regression-based classification is clear now. I hope to see you in the next video. Stay healthy, stay safe.